All right, let's talk about a real classic coding problem, one that you see all over the place, valid parentheses. Now, what if I told you there's an incredibly elegant way to solve this? A one-pass method that can check if all your parentheses, brackets, and braces are perfectly matched up without ever having to look back. Let's dive in and see exactly how it works. So just take a quick look at these two examples. The top one, empty parentheses, empty square brackets, and empty curly brackets. You can just tell it's right. Everything opens and closes exactly where it should. But that bottom one, empty parentheses, square brackets, and then empty curly brackets, something's off, right? It just feels wrong. Even though it has the same number of open and closed brackets, the order is all messed up. So the real question is, how do we prove this with code? That's the puzzle we're going to solve.
And that gets us to the heart of the problem. It isn't just about counting characters, no. It's all about the nesting. The order in which things open and close, well, that's everything.
So let's put an official name on it. A string of brackets is well formed if every single opening symbol gets closed by the right kind of symbol in the right order. The Russian doll analogy you see here, it's perfect. You can't close the big outer doll if you haven't closed the little one inside it first. It's the exact same logic. You know, this concept is so important in computer science, it even has a fancy name, the Dyke language. But all you really need to remember is that nesting is king. Now, before we jump to the perfect solution, let's talk about the trap that almost everyone falls into at first. Your gut instinct might be to just, count the brackets. Make sure you have the same number of opens and closes. And it sounds logical, right? But it has a huge, fatal flaw. And this slide just lays it all out. Look at the numbers. For both strings, the counts match up perfectly. One open paren, one closed. One open square bracket, one closed. Based on the counts, you'd think they were both valid. But we know open paren, closed square is totally invalid because that square bracket closes before the parentheses inside it gets a chance to. So yeah, counting just doesn't cut it. We have to remember the order. So if counting is out, what's in? Well, allow me to introduce the hero of this story, a simple but incredibly powerful data structure called the stack. Think of a stack like a pile of plates. The last plate you put on top is always the first one you take off. It's called last in, first out, or LIFO. And this principle is exactly what we need. Why? Because the most recently open bracket has to be the very first one to be closed. It's like this data structure was made for this problem. The whole solution boils down to these three simple rules. That's it. Rule number one, as we scan through our string, anytime we see an opening bracket, a parenthesis, a square, a curly, we just push it onto our stack. Rule number two, the moment we see a closing bracket, we stop and peek at the top of our stack. If it's the matching opener, great. We pop it off and that pair is considered resolved. If it's not a match or if the stack is empty, we can stop right there. The string is invalid. And finally, rule number three, after we've gone through the entire string, we do one last check. The stack has to be empty. If there's anything left on it, it means an opening bracket never found his partner. Okay, I know that might sound a little abstract, so let's make it super concrete. We're going to trace the algorithm together, step by step, using this string right here. Square brackets, curly braces, round brackets, and shuts all their way. Okay, here we go. We're starting with our full string on the left, and as you can see, our stack on the right is totally empty. Ready? Let's process that first character. Our first character is an opening parenthesis. Rule 1 says what? We push it onto the stack. Done. The stack is now remembering for us that we have an open parenthesis, just waiting for its matching closer. Next up, an opening square bracket. It's another opener, so we follow the same rule, push it right on top of the stack. See how the parentheses is now sitting underneath it? The stack is perfectly keeping track of our nesting order. And one more, an opening curly brace. Again, we push it onto the stack. Our stack is growing, perfectly recording how deep we're nested. Aha! Here's our first closing bracket, a curly brace. This is where Rule 2 kicks in. We peek at the very top of the stack, and what do we see? It's matching opener. Perfect. So we pop it off the stack. That pair is now complete and resolved. Moving on, we find the closing square bracket, so we check the top of the stack again, and yep, there's its partner. It's another perfect match. We pop it off, and you can see our stack shrinks again. And finally, the last character, the closing parenthesis. The only thing left on the stack is its opening partner. We pop it off, and look at that. The stack is completely empty. And that's the magic moment. We've reached the end of the string and our stack is empty. That's our green right. It means every single opening bracket found its correctly nested closing partner. Our string is officially valid. So, now that you've seen it in action, let's just quickly talk about why this stack approach isn't just some clever trick. It's actually the most efficient and definitive solution to the problem. When it comes to efficiency, this is as good as it gets. The time complexity is O of n, which is just a fancy way of saying it's linear. If the string gets twice as long, the algorithm takes about twice as long to run. That's because we only have to look at each character one time. For space, it's proportional to the maximum nesting depth. So for a string like open bracket, close bracket, open bracket, close bracket, the stack would only ever hold 3 items. The worst case, of course, would be a string of all opening brackets, which would be O of n space.
So if you ever find yourself in a technical interview and this question comes up, here's your game plan. First, explain the main idea. The stack's job is to hold on to unmatched opening brackets. Second, have that counterexample, like square bracket parentheses, ready to go to show why just counting doesn't work. Third, don't forget the edge cases. An empty string? Totally valid. A string with an odd number of characters? Instantly invalid. And finally, confidently state that the solution runs in O of n time and O of depth space. You'll nail it.
But before we go, here's a little something to chew on. What if the problem were a bit different? Let's say you have a jumbled string like 10, 10. How would you find the length of the longest valid substring inside of it? It's a much trickier puzzle, but it builds on the very same stack principles we just talked about. A really fun challenge if you're looking for one.